Electricity is one of our most faithful servants. It gives us light. It starts our cars, has unlimited in aviation, circles the globe with entertainment. It cooks and refrigerates our food. These represent few of the innumerable applications of electricity. Electricity at work. But what is electricity, and where does it come from? To answer these questions, let's look in on the world of electrons. The entire universe is composed of matter. A basic concept of the structure of matter is essential for the understanding of electricity, because the very force that holds matter together has an electrical nature. There are many different substances, each a combination of some of the 92 known chemical elements. Just as yeast, flour, salt, sugar, and shortening are the ingredients used in making bread, so are the 92 elements the ingredients of all matter. And if one of these elements is reduced to its purest, final form, its smallest unit would be an atom. No one has ever seen inside an atom. However, we think of it as a system of electrons circulating around a heavy nucleus at almost inconceivable speeds. In order to explain the principles with which we are concerned in this story, let's assume that we can stop the action within the atom. And further, let's acknowledge that this is a symbol representing the atom and not an attempt to show it as it actually is. It is impossible to show the correct relative proportions of an atom on this screen. For example, if an atom could be as large as the United States, one of its electrons would be only about 100 feet across. Therefore, to tell our story, we must resort to a symbol. Then we can think of the atom as being a group of relatively light, small particles arranged around a heavy nucleus. These are particles of electric energy. The lighter ones, the electrons, are negative electric charges. And the heavier one, the nucleus, carries positive charges. Normally, a state of balance is maintained within the atom by a positive charge in the nucleus equal to the total negative charge of the electrons. And when the atom contains its normal number of electrons, it is said to be in electrical balance, to be in a neutral electrical condition. It is possible, however, to disturb this normal balance, whereupon the unbalanced atom assumes an electric charge. Too many electrons will produce a negative charge. Too few will throw the balance onto the positive side. In order to visualize better the effect of this, let's introduce a color code in which the positive charge, or an absence of electrons, is represented with red, and the negative charge, a predominance of electrons, with blue. Then an object that is in electrical balance will be purple, an equal part of each of the positive and negative charges. We have been concerned so far with the electrons within individual atoms. Now let's see what happens when two or more neutral atoms come together. The outside electrons will no longer move exclusively within their original atoms, but will circulate about both atoms at once. And if we bring many such atoms close together, as in a piece of metal, then many electrons detach themselves from their original atoms and move freely throughout the metal. As long as the metal has its normal number of electrons, it is electrically neutral. But like an individual atom, it can lose some of its electrons and become positively charged, or it can pick up more than its normal number of electrons to become negatively charged. The electrons always try to get from a negatively charged body to one that is positively charged in relation to it. And if they're brought together, the electrons will flow from one to the other until both objects are equally charged. The establishment of unbalanced charges in matter is, in all instances, the principle of the generation of electricity. To illustrate further this principle, let's analyze the action within a cell, a simple source of electric energy. A piece of zinc is suspended in a suitable container. Its atoms are neutral until a chemical solution is added. Then some of the zinc atoms go into the solution, leaving a few of their electrons behind in the metal. The zinc becomes strongly negatively charged. Now a piece of electrically neutral copper is put in a chemical solution in another container. The copper will become very weakly negative. Since the copper has a smaller negative charge, it is positive with respect to the zinc. And if the two metals are connected, the electrons will surge from the zinc to the copper, and the charges will become equalized. This momentary current has little practical value. However, if we now connect the solutions, the charges in the solutions will become equalized, and the metals or terminals will be charged. We will then have an unbalanced condition of the electrons in the metals capable of producing a continuous flow of useful electric current. All of the work performed by electricity requires a flow of current. So let's see what principles are involved when current flows. There are three related to the flow of electricity. They are pressure or voltage, current intensity, and resistance. First, let us consider pressure. With nature always trying to maintain an electrical balance, there is a tendency for any negatively charged object to throw off or repel its excess of electrons, and for a positively charged object to attract electrons. This urge to maintain an electrical balance is potential electric energy. And since this potential energy is a repelling and attracting urge caused by opposite charges, its force or pressure is equal to the difference in the charges. It is called the difference in potential or potential difference. The unit of pressure or potential difference is the volt. The voltage, then, is always the potential difference at the negative and positive terminals of the source of the electric energy. It represents the difference between the number of extra electrons at the two terminals. And when a suitable path is provided, the potential difference causes the electrons or current to flow from one terminal through the conductor to the other terminal. To explain how this works, let's review the action of the atoms and their electrons in a piece of metal, where we saw swarms of electrons moving freely in all directions about the atoms. Substances in which this takes place are good conductors of electricity. If an outside electric pressure or voltage is applied to a conductor, the electrons will move predominantly in one direction. The effect is that electrons move from the negative to the positive terminal. This is the electric current. The unit of electric current is the ampere. 1 amp, now hold on to your hat, 6,300,000,000,000,000,000 electrons passing any given point in 1 second. Current, or amperage, then, is the number of electrons that pass a given point in a given time. And now the third factor, resistance. This factor is controlled by the nature of the material through which the electrons flow. Again, going back to the motion of electrons in a metal, we said that they moved freely about and among the atoms. However, even in the best of conductors, some of the electrons collide with the atoms, tending to retard the movement of the electrons. This is the cause of electric resistance. Collisions are more probable in some metals than in others. Therefore, different metals offer different degrees of resistance to the flow of electrons. For example, copper has low resistance. It permits the electrons to flow freely with few collisions and is therefore a good conductor. Iron offers more resistance than copper. Collisions with the atoms are more frequent. In some substances, no electrons are free to move around as in the metal. All of the electrons stay with their atoms so that no current can flow. These substances are the insulators: glass, porcelain, rubber, and many others. The collisions that the electrons have with the atoms set the atoms into more violent vibration. This makes the metal hotter. If there are enough of these collisions, the metal will radiate heat and light. Heat and light from electrical sources, then, can be obtained as the result of resistance in some metals. The unit of resistance is the ohm. Its value is best understood when its relation to the other factors is explained. A pressure of 1 volt produces a current of 1 ampere through a resistance of 1 ohm. Whatever the source or the magnitude of electric energy, these factors always have the same relation to each other. So, in order to supply our great demands for electric power, we must have facilities for generating great currents at sufficient pressures to overcome the resistance of the lines, as well as to do the work. Power for industry, transportation, and light, as well as for many other conveniences we use in our daily lives. Our own sources of current able to perform these amounts of work are the electromagnetic generators. In order to explain the manner in which electricity is produced by electromagnetic generators and used in most electrical machinery, let's have a look at magnets and magnetic fields. The Earth itself is a magnet. So are the tiny electrons. All of the electrons in any object are tiny magnets. When a predominant number of these tiny magnets point in one direction, we have an extremely small magnetized block called a magnetic domain. Magnetic material, that is, material capable of being magnetized, is made up of such domains, pointing in all directions. When these domains all point in the same direction, we have a magnet. In some materials, such as copper, the tiny magnets of the electrons never line up. These materials are non-magnetic, cannot be magnetized. Every magnet has a magnetic field. Magnets may be made in various shapes to provide convenient and strong fields. To understand how a magnetic field is useful in the generation or application of electricity, Let's go back to the electron, Mr. Electron, and watch him move across the magnetic field. Will you do it again, Bud? Now notice, as he enters the magnetic field, he's deflected from his original course. His deflection depends upon his velocity. Now, as we have previously shown, conductors have many free electrons. And if a conductor is moved across a magnetic field, the mechanical action causes the electrons in the wire to be deflected, just as we saw Mr. Electron deflected. This, in effect, establishes a negative and a positive charge at the ends of the conductor. We now have two charged terminals capable of producing a continuous flow of electric current, just as we had in the cell. This is accomplished in practice by providing a means of continuing the movement of a conductor within a magnetic field. In all electromagnetic generators, regardless of size, the same principle is used to generate electricity. The deflection of electrons in a conductor moving across a magnetic field. The same magnetic fields and forces are also used in making an electric current perform useful mechanical work. Remember that an electron moving across a magnetic field is deflected. If the electron were moving in a wire, as when electric current flows, the deflection of the electron would cause it to push against the wire, tending to move the wire. Billions upon billions of these tiny pushes combine to provide the force. The stronger the current, or the greater number of electrons, the greater the force moving the wire. These forces on current-carrying wires in magnetic fields furnish the power for all electric motors, from the simplest to the most complex, from the smallest to the largest electric motors. The principle is the same. The deflection of electrons flowing in current-carrying wires by magnetic fields. In fact, interaction between the magnetic fields and the electrons is the basis of all electric devices. And now we may summarize that the billions and billions of atoms of which the universe is built are composed of positive and negative electric charges. That these charges are normally balanced in matter. That by unbalancing these charges, electric energy is made available. That the urge of nature to restore this balance creates electric pressure. And that the response to this urge, the action of the restoration of the balance, is a flow of electric current. The flow of electric current, then, is simply the movement of electrons away from objects that have acquired a negative charge to objects whose charge is relatively positive. It's this principle that has made possible the countless electric devices which contribute to the comfort and fulfillment of richer and happier living today. Devices which will expand that to unlimited horizons in the future. Devices whose operation is dependent upon nature's design for matter, demanding that matter itself shall always seek a state of new electrical balance.